Welcome to the third session for today, and we will continue with earphones.
Hello, do you hear me? My name is Renaldas Zioma, and I will talk a little bit about the iPhone, maybe a little bit more in depth about the rendering, about how the OpenGLES works inside. I'm an iPhone technical lead at Unity Technologies, and before that I was working on Xbox 360 and PlayStation 3 on the Frostbite engine. And during that, I did a couple of demos for Amiga and PlayStation Portable. You might see them. So I will be talking today about, okay, so first of all, why I started looking into inside the driver of OpenGLES in the iPhone, because we noticed that the performance is louder. Okay. The performance scales on basically on the CPU side. It was taking it was proportionally taking the same time as the number of vertices you would be sending, and that became quite scary. So I started to look in the drivers. Another thing is, it's very interesting to look inside the driver, because then you can understand what GPU actually is doing and what language kind of it speaks from CPU to GPU. It's of course not OpenGLES, it's something completely different when it sends the commands. So it's interesting to look at that. And fun to look at assembly. There are number of, if you are looking at the question how actually CPU and GPU communicates, or what GPU can do nowadays, there is a quite good documentation from the ATI about the hardware. It's quite in depth. There is a Nouveau project, open source project, that people went and reverse engineered NVIDIA cards, NVIDIA drivers, and it's quite interesting to look at. And if you work with the PlayStation 3, then the libGCM is really good, very small abstraction on top of the command buffers, and it's really easy to see what's happening in there. And you can look at the PlayStation Portable Homebrew SDK, because it was as well reverse engineered, and it's pretty easy hardware, and it's really interesting to see how everything works inside. And another reason to reverse engineer with the iPhone is because Apple is very secretive, and they don't really say what hardware is inside. So it's always interesting to see what it is actually inside and what it can do, because it can actually do more than the OpenGLES 1.1 and what they say it can do. And on the iPhone, reverse engineering on the iPhone is fun, because their ARM assembly is very easy, and the SDK provides really sound debugging tools. And the GPU of the iPhone is PowerVR MBX. It's a quite old hardware. It's quite simplistic hardware, and it's a really good point to start, because modern GPUs are very complex. If you look at the ATI documentation or the NVIDIA, you see lots of stuff in there, and in the drivers they do lots of workarounds for features which don't work or are screwed in the hardware. So it's really hard to understand those drivers, but it's really easy to do that on the iPhone. I do just a brief introduction in what iPhone hardware. I'm pretty sure everyone knows that, but just there is a CPU, which is ARM v6. It's paired with the VFP coprocessor. It's a CI-SIMD coprocessor. And on the CPU side, there is a small problem. There is only L1 cache, and the memory is quite slow. So the memory bandwidth is usually a problem on the iPhone. And on the GPU side, we have a PowerVR MBX Lite with the VGP Lite. MBX Lite is a rasterizer, and the VGP is the thing which can actually execute the vertex shaders. So it transforms vertices. Though you don't have access to the vertex shaders via the OpenGLES right now. And the one interesting thing about the VGP and MBX, VGP is it's not like usual GPU. You put the vertex in and you get the result, like you send a triangle and you get the result on screen at the same frame. However, MBX and VGP, they run in parallel. So whatever you send to VGP, it will be rendered on the next frame. So VGP will transform vertices and it will store it somewhere in the memory. And the MBX will grab it on the next frame. They done that in order to get better parallelization. And the talk today will be only about the MBX and OpenGLES 1.1. It's not about SGX. SGX is completely different inside, and it's not that interesting. It's interesting from another point of view, but the drivers there are much better, so it's not that fun to hack them. And yeah, we just go directly into and see what's inside the GeoDraw arrays. There is assembly here, but what's interesting here is immediately after we go inside the debugger, inside the GeoDraw arrays, there is like a prologue, and then there is one interesting line which calls this get TLS value, which basically gets some value from the thread local store. And if you start looking into that, you notice immediately that there is some connection, and that's connected with the EEGO context, which you set. So basically what driver does, the first time you set the context, when it enters the GeoDraw arrays, the draw call function, then it will fetch this context in some way. Or more specifically, it will fetch not the context, but it will fetch something inside that context, which is like a private structure. And so as soon as we know that, what we do is you will go and you just start analyzing, you just draw things, and you compare, because we know, okay, that the draw array is interested in this context, and that context is actually stores all the a state of the driver. So what we want to do is we will draw a draw call every time, and then we will just compare how the internal state of the driver changes, and we can say things from that. And if you just do a simple draw call, you will notice, I don't know if you see here, there's like a red thing is here, which show that in the driver state, there's only 2 addresses which change. The driver state is it's pretty huge, it's several kilobytes. But with the draw call, you will notice that only there's an increment in the address. And of course, you immediately can go and see, so what happens in that address if you follow that pointer. And you see that the driver is incrementing that, and it's writing something into this memory continuously. And actually, that's it, because if we rearrange this data, you can start seeing from that pointer, there's some block here and some block. And if you look at the hex, you probably can recognize what's in here. Well, I just convert it to floats. And you more or less immediately can understand that is the matrix. That's a world matrix. It's transposed. So the positions, the translation are here. That's a translation vector, and that's a rotation part. And afterwards, you can see that's the I was sending a simple quad here, 2 triangles, simple quad, which you can see the data here. That's the vertex data, that's the positions, and that's the UV coordinates here. So that's actually how it works. And the GPU will go, this data will be sent to the GPU, and that's what is called command stream. Well, in some other hardware, you might have known this name from command buffer or push buffer on the Xbox, the old Xbox. So, but essentially, all the drivers on the old GPUs more or less work in the same way. They keep some state, they do some weird things inside, but what they do, they just fill in these command buffers, which GPU will go and interpret in some way. So, for most of the GPUs, it's actually, this buffer is a ring buffer. So it goes like a ring here, and on this side, you can see a driver. So it basically, there is a right pointer or put pointer in language of drivers. And so driver is always writing here and going this direction. At the same time, this is like a huge buffer here. The GPU is somewhere over there, and there is a get pointer. That's the place at which point the GPU is reading right now. So the driver is writing here and goes forward, and the GPU is like running behind and is trying to catch up on it. And once they catch up, that means that the CPU is not fast enough, and the GPU will stall until there is enough commands put here. And if the GPU is too fast, CPU is too fast, then it can caught on with the GPU, and then the CPU will stall, waiting for GPU to finish. There's a slight difference on the iPhone because they are not ring buffers, but a double buffer. So instead of having this ring buffer, one frame, the driver will write into one block of memory, and then it will just swap, and the GPU will be accessing one, and the CPU will be writing into another. And that leads to the question, so what the GPU does. And quite usually, if you look at the structure of the GPU from inside, you will see like on the entrance, there is a command processor. And that's thingy which actually streams in all these commands and parses them, and then sends them to other GPU modules. So you can see like a complicated modern GPU there with lots of blocks, but you can see like a command processor on the top which sits on the bus, reads it and sends to setup engine, and then goes into to the actual shaders here. Okay, so now we can go back to our GeoDraw array. And we can see what's going forward. We can see what's happening inside, and there is quite a lot of debug information in these drivers. And I'm using usually the old OS, iPhone OS 2.0 because it's a little bit even easier to read it. But there is a slight difference between newer drivers, but more or less they work in the same way. So if you look down into the GeoDraw arrays, we see that it calls some prepare to draw. And prepare to draw, it's actually what it does. If you set the states for the OpenGeoES, it does actually nothing. Oh, it does nothing to GPU. Internally, it accumulates the state. And once you issue the draw call, then the prepare to draw will actually send this accumulated data, and it will put it into this same command stream. And later we see that the draw triangle strip is invoked, and then it checks if there is enough space in the command buffer, and then it says emit start triangle strip. And that is like a header of the packet, it just says, it's 8 bytes, which says, okay, we will be rendering triangle strip now. And then there is this copy data afterwards. And that's a very interesting point here. So we look inside what the copy data does, and it actually does what the name is. It copies the data. So it's very funny. It just takes your data, you put into the vertex buffer, or if you use the client arrays, it will just copy all this data and put it inside the command stream. And it will do that every time for every draw call. And if you start looking into the code which does the copying, it's pretty funny, because it does for each vertex, for each component of that vertex, and I mean component position, texture coordinate, normal, it will do this thing, it will analyze, so okay, I have 2 components in my case, position and texture coordinates, and it will fetch from some structure internally, okay, so this guy, me, asked me to render texture, this geometry. So I know there's 2 components here. So I would check what's the size of the component, and I will check what's the stream pointer for this data. And then it will go and calculate the offset, and then it will do some, well, basically it will switch on type and jump. There's like a huge case there with lots of different types, basically. And it will switch, and it will jump for each component, and it will load the data from my pointer, and then it will jump to other point, and it will store the data inside this pointer, R0 here. It points to IP, in this case, points IP on the ARM, it's an intermediate pointer. So it will point to my data. And R0 in this case is a stream buffer, command buffer address. So if, yeah, one thing, I never noticed any prefetching inside this driver, which is pretty bad to my understanding, but I don't know. So ARM has this really good instruction, PLD, which is probably means preload. So we can preload on the address with some offset. So you always, it's quite easy to do prefetching ahead of you once you are reading the data. But driver doesn't do that for some reason. And if you rewrite this code in C, like I just tried to write this. So that's the, you have like two loops here with the bunch of stuff and the switch. And that's what driver does for each vertex. It's pretty expensive. OK, so you might ask, so the VBO, that should be a solution. But if you've tried the VBO on the iPhone with the MBX hardware, you notice that with the SGX, it does increase performance because the driver and the hardware is completely different. But on MBX, it doesn't do any difference. And people were saying, I saw that on the forums, so probably Apple is smart enough to optimize that for me. And that when I use the GeoDraw arrays or draw elements, it's as fast as draw static, like static VBO, because Apple did some optimizations. But in reality, it's other way around. So there is no optimizations, and the VBO just copies the data, even if it's a static. And the reason why it does so, because actually there is no like when you say to OpenGLES, I have this stream data, that's how my vertex data looks like, right? But once you set some states, then it might require a different data for you. For example, you haven't for example, I'm rendering my sprite, which has no normals. But if I turn on the lighting, then it has the GPU will actually need a normal information. So the driver will go, and while copying the data, it will insert the normals. Even if I haven't supplied them, it will insert like a default 001 normal. And that's why the VBO the VBO cannot do any optimization, because at the point when you specify VBO, it has no idea what TNL state will be while you will be rendering it. And that comes from the limitation of the MBX. MBX doesn't have a usual, the modern GPUs have like a vertex stream fetcher thing which can be set up to read the vertex data. And MBX doesn't have that. So MBX, all the commands, all the data comes through the single port, and they must be pushed. So there is no like way to read from different points in memory. So that's why driver does that. And actually, the same happens with, I used draw arrays before, but it's just it's a little bit simpler than the draw elements. But essentially, they do the same. The difference with the draw elements is that MBX has no support for the index buffers at all, the GPU itself. So the driver will just simulate that. The same happens on the PSP, actually. So they will just indirect read use the index buffers while copying the data, and they will just jump in the source stream according to the index and store that. So the GPU will get just a vertex array at the end. So yeah, so if we just try to push as many vertices as possible into the GPU, on the iPod Touch 2nd generation, we can peak it at 1.7 million vertex per second. At least I could do that. I don't know, maybe you can do that even faster. It depends on the size. The size of the vertex was 12 bytes here. So, but if you measure how much time it takes for the OpenGOES on the driver side, on the CPU side, to push exactly the same amount of vertices, if you want, basically, if you would do a demo where you want to push as many vertices as possible, then you will notice that it's like 64% of second, the driver will be just copying the data. So they do work in parallel, though most of the CPU is already too busy fetching the data into the GPU. OK, so we just continue with reverse engineering from that point, because we see the problems. And it's quite easy. Basically, as I said, you just use OpenGOES to set state, and then you just draw a very simple couple of polygons geometry, and then you just dump the context of the driver, and you dump the stream buffer, because now you know where it is, and you just simply diff it, and then you can figure out everything quite easily, because you know what you send, and you know what you get in the stream buffer, and you can immediately analyze what data is sent and in which case. And it's sent in these packets, and these packets are written into the memory. And just by looking at that data, you can figure out that the first 4 bits like it's always in the 4 bytes, 32 bits. The minimum unit of data is 32 bits, and the first 32 bits in packet usually start with the 4 bits which determine the packet type. So we have like 16 different packets. And that's the first command, but first packet you will usually find. It starts with A, and it's actually for uploading data into the registers, into the vertex registers. And you see like it has a 1 byte for the register, for starting register, and 1 byte for the ending register. And afterwards, you will find out lots of data. I actually can, just for a moment, I can briefly jump back. Yeah, you see here. So that's upload data, starting from 0th register up to the 3rd register, and then it uploads like chunks of data. And that's another packet, starts here. So that's for uploading matrices usually, and that's for drawing the primitives. And that's the primitive you will find. It's a triangle strip, and it's 4. It's a number of other ones. And yeah, and for example, you're writing triangle strip, and at the end it will put 3. That means that the strip should stop, and then the next packet will follow. You could put 2, and 2 will mean restart strip. That means that the packet will continue afterwards, but the GPU will stop strip and will start another strip. So you don't need to have like a multiple draw calls in this case. And the command stream will finish with F on the end. That means that GPU knows that that's the end, and the CPU will wait. For example, if you look deeper in the driver, you will see that the CPU will wait after it sends all the commands. And for example, if you do like a GL finish, then it will sit and wait until the GPU becomes free. And the GPU becomes free after it hits the F. And there is one other interesting thingy, a packet which starts with 9. And it looks very much like actually uploading the vertex shader. For example, if you just enable a light and then you do a draw call, you will see that like there's several packets with 9 uploading to some, and it has addresses in there, and it's uploading something which looks very much like a vertex shader. Okay, there is one interesting limitation inside, that the packets cannot be longer than some length. 12 kilobytes. It looks like 12 kilobytes. I don't know, but if once I was looking in the driver output, it was usually always in 12 at least 12 kilobytes. So then it will just insert another packet. So if your Joko is very long, it still will be subdivided in smaller packets, like this cat with lots. Okay, so from this knowledge, we can figure out what's the best way to submit geometry with the OpenGLES. What's the really best way, not what is written in documentation, which usually is just a generic docs, which are provided for hardware and not for the actual driver implementation. So the best way to submit geometry, because we have a strip restart thingy, the best way would be to use the index, to start with doing a very long strips and indexed strips, but do not concatenate them with the generates, but just keep lots of strips. And then, then sort your vertices in the vertex buffer to follow the order of the indices. So it just helps with the CPU cache, because once it will be copying it. And then you will convert index strips to, from index strips, go to the index triangle list. And that's really interesting point. If you look at the, if you issue goutDrawElements command, and you would say, render me triangle list. If you look at the command buffer, you see that it still renders strips, not triangle list. Because driver is smart enough to analyze how the indices are laid out in the triangle list. And if it sees that they are reusing like a previous two, like if the triangle list is actually a strip inside, it will convert it to the strip. And once it finds a way, finds a place where the two triangles are not connected, like not in a strip, then it will put the restart in there. So if you would just create a index strips from the start and insert degenerates there, you would lose like a one vertex for each degenerate. And it's a little bit more efficient if you do that as a triangle list, because then the driver can, instead of you putting two degenerates there, it will put a restart. Oops. Okay. So we know how to send the data now to OpenGL, and pretty in the best way for a driver. But the next step, we want to actually do the works ourselves instead of relying on driver. And what I will be showing here, I'm not sure if it's a, I'm not sure if you would put that in the game. I'm not sure if that would go through the App Store, and it could. I haven't tried that, but it might be interesting for demos, for example. And the one thing is that it relies on how the data is put inside the driver, and driver might change from going from version to version. It doesn't change completely, but for example, going from 2.1 to 3.1, like the offsets changed by 4 bytes. So it's like you need to check what's the OS version you're running on, and then you can do patching different. So for patching, we just use OpenGLES to do all the dirty work, to set all the states, to allocate all the internal structures. And to do that, we set all the states, and then we just render simple geometry, for example, at the start of the frame. So then it will flush all the state. And we can actually, on the first couple of frames, we should render a lot of geometry to just allocate all the buffers, so the command streams are big enough already. And the next is like we just write a very simple function here, which gets this context. It actually, instead of using the thread local store, it will just look in the context, find the offset, and grab the pointer it needs. And from that pointer, we can find out the pointers for the command stream. And we just memcopy our block in there, and then we just patch these 2 pointers. And that's it. And we get pretty simple API instead of bunch of blah, blah, blah. It's just always the same function. And you just copy the data and you just patch 2 pointers. Yep, and it's 3 times as fast for the simplest geometry. So I'm using the same 12 bytes, and it's already 3 times as fast as the OpenGIS driver. And if the vertex is becoming bigger, and more work needs to be done on the driver side, then the time on the driver will increase. So we're actually bound by the memory bandwidth here. But memcopy will be bound by the memory. And you will not be able to render more, actually, because there is a limit how many vertices the GPU can render. It's like 1.7, for example, million vertices per second. But you will be able to do more stuff on CPU, first of all. And second thing, because because we are memory bandwidth bound, when we are copying our data into the command stream, we can actually interleave that copy with the VFP code. VFP is a coprocessor which you can do skinning or some other stuff in there. And it can hide some latency in the data access. And you can, at the same time, you can you can prepare your data for rendering, like copy it in this command stream, and at the same time you can skin it. For example, if you would be doing the skinning in normal way on the VFP, then you would just, on CPU side, usually you just skin the vertex and put it into some buffer, and then OpenGIS comes and it takes from that buffer and it puts it again. So in this case, we can save 1 copy, we can write directly into the command stream, and we can use the latency of memory access to interleave it with some math functions. Yep, and that's basically it about the command buffer patching. As I said, you should use it on your own risk if you want to. It's maybe only for demos, and you should be careful because if you change some states, then the data which you send needs to be put in the way GPU imagines it. For example, if you enable like a lighting, then you will need to add the normal, even if you don't have a normal in the source stream, you will have to supply it with the default. If you don't do that, you will see that the rendering is completely screwed. Or you can actually just kill the device, like you will need to hard reboot it afterwards. And I just want to compare the next couple of slides. I just want to compare the skinning on GPU with the CPU. And if you look at the VGP, as I said, it's the unit on the GPU side which does the vertex shader processing, and it runs on the lower frequency rate comparing with the CPU. It runs on 133, and with the small vertices, we can peak it at 1.7 milliverts. And if we divide that, we can see how many cycles each vertex takes. And it seems like it takes around 80 cycles on the VGP to process 1 vertex, which seems to be a little bit too much. I don't know, maybe VGP is running at the lower frequency. Maybe something, maybe it's actually very generic shaders which are used inside the driver, and maybe that's why it takes so long. But I don't know. And you can use only 9 matrix palettes for skinning on GPU. So if we compare that with the CPU, we have this VFP unit, which usually is used in a scalar mode for just like a floating point unit, but you can switch it into the vector mode. And then the one multiply add will take around 2 cycles, and the latency is 7. And more or less, like, not really optimized shader not really optimized code for the skinning will take around 40 cycles per vertex. You can do it better than that. And if we divide the frequency rate at 40, we'll get that we could, in theory, peak at 12 million vertices. In practice, you will not be able to do that because of the memory bound. You will be memory bound. However, it will be a number of times faster than the doing skinning on GPU. So yeah, just use VFP. That's it. Do you have any questions? It's pretty simple. Yeah.
Yeah, I have a quick question. Right now, I'm writing my own engine for the iPhone, and I'm currently passing down around 18K of vertices to GL vertex pointer, but to GL draw element, I'm only drawing n amount of quads on the screen. But it seems like I'm still getting the same frame rate, even though I lower the amount of vertex count that I pass to GL vertex pointer, or whether I increase it or lower it, doesn't change a thing. I mean, does it matter how much vertices you pass down to GL vertex pointer? Does it always copy all of them?
No, it will copy only
the one you pass to GL draw element, right?
Yes. Or only if you use index buffers, then it will copy only the amount, the indices you have. And if you use GL draw arrays, then the amount of this, the size you want to.
Oh, okay.
Number of elements. Yeah.
That's it.
Okay. Yeah. Thank you.
Other questions? Time for one more? No? Okay. Thank you.